All right. Welcome, everybody, to our study union session. I am Brendan. I am the tutor. So for those of you following at home, welcome. Just to let you all know, we might be doing this study union session a little bit differently than some of the other ones you've seen before. I'm going to poll the room and see what those who are here in person want to see. So what I'm going to explain is I have some problems that are ready to go on the Study Union WordPress site. So if you go to www.ucfstudyunion.wordpress.com, under Engineering, you scroll down a little bit and you will find a Word document that has practice problems pulled from the textbook that anyone can practice and do on their own. They do not have answers with them right now, but they are there for you to practice. Now, I was going to work as many of those as I could here in the session. The problem is I don't have the textbook, and I don't really have a way to display the computer, so you couldn't actually see them. I'd have to draw them on this board, and it would take extra time and some stuff. Additionally, I heard that the session earlier today done by Mohr was a lot of just practice problems, and I have been tutoring solid mechanics for a very long time. I have done study union sessions before where I'm just running through a lot of practice problems. And all of those past study union sessions have also been live streamed and recorded. If you go to youtube.com, search UCF Study Union EGM 3601, you can pull up 3 or 4 2-hour study union sessions from the past. So what I'm considering doing this time is actually asking you all, what do you want to see from more of a conceptual level, right? I will still work like some examples of concepts, but I won't necessarily pull like a set problem from the book, right? And the idea being you have plenty of access to practice problems. You can look in your textbooks. You can go on Chegg for answers. You can look at the past study union sessions on YouTube. You can look at the past reviews I've done for this class on my WordPress site. My feeling is just doing more practice problems may or may not be beneficial if you don't understand the concepts. So do we want to see kind of that more concept-based session? Does that sound good to everyone? Awesome. Okay. So in that case, I'm going to make this kind of really as interactive as I can be, in that what concepts do you all have trouble with? What concepts do you want to see? So before the session started, I did get a couple of requests. So we want to see a little bit of, this marker is dead. We want to see a little bit of establishing Q for transverse shear, right? So from trans shear, what the heck is Q? How do we establish it for different shapes? Doing some examples like that. And then I believe we also said we wanted to see a little bit of I as well. So those moments of inertia and how they were working. What other kind of concepts are we having trouble with? Mohr circle. Cool. What else? Macaulay functions. Cool. I know that that's spelled wrong, but whatever. Deflection. Okay, so deflection and Macaulay functions are kind of go hand in hand, so we'll talk about those kind of as one thing. Anything else? Yes?
I'm not sure what it's called, but it's the equation where it's like DI and then like a double integration method.
So that is deflection via the what I call the successive integration method. So again, we'll talk about that with the Macaulay functions. You said you're in mechanics of materials. Who teaches that?
Dr. Macaulay.
And that's a class we have here on UCF campus?
Yeah, it's basically the civil engineering version of solid.
Oh, okay, that's cool. Okay. Do you all go over the Macaulay functions, just as a question?
I don't recall that, that's why I was wondering.
Okay. Do they call them the discontinuity functions, by any chance?
Where it's like boundary conditions like for
Kind of, yeah. Here's, and we'll talk about why I do that in a second. When we get to that, we'll go over some stuff about it. Okay, so let's just go ahead and jump into these 4 things. If we've got some extra time, we can throw up some more concepts, so on and so forth. Okay, so let's talk about Q first and foremost. So what is Q? Does anybody know? It does, in fact, have a name. Does anybody know what that name is? Exactly. It is the first moment of area. There is a second, and I think there's a third, but we don't care about those, right? So it is called the moment of area, It is different than the moment of inertia. Unfortunately, so for those of you who were in my dynamics session about 30 minutes ago, we went over what a moment of inertia was. I have done that as well in the past for solid mechanics. As far as what moment of area is from a conceptual level, you got me beat. I actually don't know what this is. I can't do the lovely in-depth explanation of it the way I did for moments of inertia, so I do apologize for that, but I do know how to calculate it. So when we are doing transverse shear, right, we have some cross-section. In this case, I'm going to start with the generic rectangle. So what is Q, right? First of all, how does it factor into the equation? What equation uses Q? Right, VQ over IT, right? And that is what does that actually establish? Thank you. Okay. What does, say again? Transverse shear stress. That is correct. It is shear stress that is developed by a transverse shear load, right? And so we get that equation. Okay? So that big Q, right, is this first moment of area. Now, what is, or more importantly, does shear stress change with location on the cross-section? In other words, is the transverse shear at this point the same as the transverse shear at this point, or at this point, or at this point? Is it? Is the value of it the same? So you say Q is different. So if Q is different, can the transverse shear stress be the same? I'm sorry. Yes, the load is the same. I'm talking about the shear. Is the shear stress the same at all those points? No. Okay. Yes, my mistake. So how we deal with those, right? First of all, let's establish some nomenclature just so we are all on the same page when I talk about things. So let's call whatever point we're looking at the point of interest, right? So our point of interest establishes where we want to find the shear stress. Where is shear stress maximized? Yes and no. Neutral axis, right. Which passes through what? Not the center. Centroid. What's the difference? Kind of. So there are three centers that you can deal with in physics, right? There's the center, there's the centroid, and there's the mass center, okay? Center is based purely on this dimension, right? In other words, half of the height is the center, right? Or halfway this way, right? Half in both directions is the center, okay? In the case of a rectangle, that makes no difference. In the case of a trapezoid, right, if this is the height, and it's symmetrical, right, center is at 1/2 that height. Centroid, right, is the center of area. Okay, so it may also be called the area center. And that is based on the distribution of area, right? So in a rectangle, center and centroid are the same thing. In a trapezoid, that is not the case, right? In a trapezoid, there is more area below on this lower half, so it pulls your centroid down a little bit, right? That's why your centroid and your neutral axis for trapezoids, right, is down here. The important point is that the neutral axis passes through the centroid, not the center, right? There is also a mass center, which is very similar to the area center, but based on mass distribution, but we don't talk about that in this class, right? We don't care. Yeah, there's my eraser. Okay. So yes, as we said before, the stress developed by transverse shear is maximized at that neutral axis. Okay. Why is that the case? What value within this maximizes that? Maximizes at the center. I'll give you a hint. Q, yes. So let's talk about Q. How do we establish Q? What is it? If we're looking at this point, if that's our point of interest, how do we establish Q?
You would get the area above the neutral axis.
Okay, so wait, I have a red marker for this. Let's use colors. Hopefully this one works. That's the area above the neutral axis. Times that. Is that the Q? So, question. Never mind. Yes. Okay. So, the way that I explain Q when I tutor this in my sessions, how do you find Q? There is a process, and it goes like this. First, you go from the neutral axis, right? You've got a point of interest. So you go to your point of interest. Oh, look, a real eraser. Cool, thank you. You go to your point of interest, and you draw a line parallel to your neutral axis. All right. So you then have to establish two things. First of all, what is the equation for Q? Summation of YA. It's both. It is actually Y bar prime A prime. Okay, so yes, we're looking at the correct values, just with some different fancy things to establish them. Right? The primes mean that they are not for the overall shape; it is for some other thing. Right? So the A prime is what I call the area of interest. Right? So where is the area of interest for our shape? From the point. Not quite. That's a good idea, and it is based about a point, but it's not the smallest area necessarily. Yes? We'll talk about that. Yes, but we'll talk about that in a second. Let's establish the area first. Yes. So the area of interest starts at your point of interest and goes to the edge of your shape away from your neutral axis. Okay? What that means, go to your point. It is the area to the edge that is away from the neutral axis. The way I say it in that very confusing manner is because if your point is below, right, I don't want to say it's the area above it, because in this case, above would be wrong, right? It is the area to the edge away from the neutral axis. Does that make sense? Always away from the neutral axis, right? There is only one condition that your area of interest will ever touch your neutral axis. What is that condition? Your max, right? You are looking at a point on the neutral axis. Okay. So now that we've established A prime, what is Y bar prime? Correct. It is the combination of you two is correct. It is the distance from the neutral axis to the centroid of that area of interest, right? The prime there means the interest, right? So it is the area of interest, and it is the centroid, the Y bar, of your area of interest, prime. So if we're looking at this top one, it is not, I'm going to draw it in red so we know it's not this distance. Okay? A lot of students think it is the distance to the point of interest. That is not correct. It is the distance to the centroid, let's do it in green since we have that now, from your neutral axis to your centroid of your area of interest. Okay, so for rectangles, right, these nice easy shapes, does that make sense? Okay, now let's do some quick examples of not so nice shapes, right? So the common other shape is what? Circles, right? And so for circles, it works the same way, right? The only problem is that the centroid calculation becomes a little messy, right? In other words, if this is your point of interest, right, and you establish your area of interest, how do you find that area and that centroid? The honest answer is you probably don't. I believe that's actually above the pay grade of this class, in that when given a circular shaft, you are almost always going to be asked to establish it at the neutral axis, right? You're almost always going to be asked for T max in the case of shaft design, right? Now, for a semicircle, that becomes really easy then, right? Because A prime is just half of your overall area, and Y bar prime is just the centroid of a semicircle, which if you look in that table on the back of your book, it's there. Or if you look it up on Google, it's also there, right? And so that Q becomes rather easy. Now, what happens if we have an annulus ring? So first of all, does everybody know what I mean when I say an annulus? Cool. It's a hollow tube, right? That shape is called an annulus. So what happens if we have one of these guys, right? If we establish the max, right, the max is still there, but what is our area? Right, it's this, right? How does that affect Y bar prime? Not quite. It actually stays down here. It is below that ring because there is area of the ring below it, right? It is the average of all those areas. Can anybody think of a way to find that? Yes, the Y bar prime. So how did we find A bar prime again, or A prime again? Yes, you can. Centroids are subject to the law of superposition. Ergo, right, if you have a composite shape, which you can call this a negative composite, right, you can take the sum of the centroid locations, or in this case, the difference, right? So you can say that Y bar prime is equal to the Y bar of the outer ring minus the Y bar of the inner ring. I guess these are technically prime, right? And so that then becomes your Y bar prime in the hollow tube case for transverse shear. Yes, your face looks a little bit confused. Are you?
Oh, no.
Okay.
I actually never seen this before.
Yeah. So imagine that that's like a big cylinder and there's a hole in the middle of it, right? It's a hollow tube, like PVC pipe or something like that. Yeah. All right. So now, are we comfortable? A little bit more comfortable with how to approach some of the more complex shapes and finding their cues. Right? Are there any other particular shapes that you all want to see? An I-beam. Ooh. We can. I-beams are definitely yucky. Right? So in an I-beam, I'm just going to draw the top half of it because let's assume that we're looking for the max one, right? Okay, what are they?
Getting the big square and cutting out the two hollow bits. But that's for I.
So that's for this. That's for getting I. It doesn't work as well for Q. Yeah. So in this case, right, the area is fairly straightforward, right? You got, area of the top plus area of this little bottom bit here, right? So is A prime going to give anybody issues? Okay, so Y bar prime. How do we treat Y bar prime of this? Say again? For right now, let's assume that we're looking at a point on the neutral axis. you find the y bar prime for each of these guys, right? So for this one, it's going to be there. For this one, it's going to be there, right? And you add them up, right? Yes. So I had to sit there and do that in my head for a second. But yes, you add them up because we're subject to the law of superposition, right? It's the same way that you did it for the overall I-beam, right? When you have an overall, or it's more akin to a T-beam, right? This is essentially a T-beam. So you do your sum of the y, right? It's, what is it? Sum of the area times the individual y bars, right? Over sum of the areas. Actually, I'm sorry, that's how you do this one. It's not just a direct, it's not direct substitution into superposition law, right? In other words, it's not just y bar prime of this minus, or y bar prime of this minus y bar prime of this. You have to do it this way. You have to do the sum of the area times the individual y bar primes. Does that make sense? So in other words, for this guy, right, you'd have the outer ring. So you'd have area of a semicircle, which is 1/2 pi outer radius squared, right, times his centroid, right, so times his y bar prime, or y bar for the outer, minus 1/2 pi r inner squared y bar inner, right, over 1/2 pi r outer squared minus r inner squared. Right, because you have to do it in this form. I kind of lied to you before. Y bar prime is not directly subject to the law of superposition. It's this summation thing. Right, and so in this case, you can see you just take the area of this guy times his y bar plus the area of this guy times his y bar, all divided by the sum of the areas. Yes?
Let's say, on my previous exam, we had like a ID, but the bottom was like smaller than like the top.
Yuck.
When you're finding like the y bars, it depends on what the point is.
Yes.
Do you take like the lower half or the top half?
No. You just take the half that you care about, right? Because remember that the y bar prime in this equation is relative to what? So it's the point of interest relative to the neutral axis, right? So we only care about, in other words, you are establishing the neutral axis as your 0 point, as your coordinate. You don't care what happens on the other side of it. Does that make sense? It's not always the smallest area, right? It's just the area to the edge away from your neutral axis, right? So in other words, let's say that this wasn't symmetric, right? Let's say that we had something like this, where down here it goes way bigger, right? If our point of interest is here, right, we don't care about any of that, okay? We're only looking at the stress developed at that point. And the reason that this happens, right, is that you are looking at a cumulative stress, essentially, of everything above that point, right? Because remember your stress profile, right? If we look at this from the side, right, here's a profile view of it, right? At the edges, what is your shear stress? 0, right? And we maximize at the neutral axis, right? So you're looking at, if we're looking at, right, and it's, remember that these arrows do not show direction, they just show magnitude, right? And so, if you're looking at a point here, essentially what you're doing, it's not a direct summation, but you can think of it that way. A kind of combination of everything, all the stress that's happening above that point, right? And so it literally ignores everything else. Does that make sense? In this case? So in the case that we are unsymmetric and on the point of interest. So, on the neutral axis, right, what happens? What are we looking at on the neutral axis with our shear stress? Area above is equal to the area below. So the A bar prime doesn't matter. Okay? Does the Y bar prime matter? Is the Y bar prime going to be different? Is the distance to the centroid of this going to be equal to the distance to the centroid of this? Is it? So, right, how much area is down here, right? We've got a lot more area kind of pulling down there, right? So what you're probably going to see is something like that, where this distance is way larger, right? So if the areas are the same, but the Y bar prime for this one is larger, then the Q for which side is larger? The lower one, right? And if the Q for the one lower is larger, does that establish a more max shear stress? Yes, right? So you take the larger area in that case. Actually, wait a minute. I just had.
Because if the area is the same on the top and the bottom.
Yeah, how can you? You can't have an object that is unsymmetric about the neutral axis like that. Not area-wise. Yeah. You might have it where it's unsymmetric about your point of interest, but not about the neutral axis, now that I think about it. Yeah, it's at the centroid. It should. It definitely should. And yeah. And so even in the case of I-beams, that's what you should see. Do you happen to have that problem? The one that you were talking about? Okay. So while you're looking at that, we're going to kind of, we'll try and move forward a little bit. But is everybody now kind of comfortable with that Q and how we establish that, right? The other thing is, on the final exam, I understand that there's more time, but the questions are not usually much harder, per se, right? There's usually a little bit more involved. They're longer, and there's a couple more of them, but you're not going to get some ridiculously out of nowhere shape that you've never seen before on a final exam, right? On finals, they tend to be more regular shapes where you can either really quickly reference a table to find some of this information, like your Y bars, or the things that you are expected to know, right, or expected to have written on your formula sheet. Is that good? Are we good with Qs now? Aside from the one problem that we're going to look up a little bit. Okay. So if that's the case, while you're looking that up, I'm going to move towards I's a little bit and establishing those moments of inertia. So for those of you who were just in my dynamics session, we talked about this before. How many moments of inertia are there? 2, right? There is the one that we deal with in this class, which is right. So this one is the area moment of inertia, and in dynamics, you do the mass moment of inertia. So for those of you who were just in my dynamics session, forget everything we just talked about. Now we're switching over to area moments of inertia. So the general form of the area moment of inertia, right, is what? So that is for a specific shape. In the general sense, right, they take on, does anybody know what the general form that they take on is? Again, that's a specific case. So in the general form that they take on, if I'm not mistaken, it is an area integral of something. I believe it is some distance, so it's an area integral of some distance squared, right? So this distance is, a radius or the length of a side or the distance from something, and then you take the integral over an area. You did this back in statics. In solid mechanics, we almost never do the integral version because we use nice, pretty shapes that have this all done for us. So everybody was mentioning the 1/12 bh cubed. What is that the area moment of inertia for? Say again? Rectangle, exactly. Now, which one is the base and which one is the height? Sorry, cubed. Okay. So this would be base, and this would be height, right? What is that? Which axis is that about? A horizontal axis, right? If we wanted to do one about there, what would we do? B cubed times h, right? It flips. Oops, I'm sorry. B cubed times h, right? The way I like to do it, this is how the book teaches it. I actually kind of do it a little bit differently. I say that you just have to memorize this form. Just memorize 1/2 or 1/12 bh cubed. Your h, right, your height, is always the side that is perpendicular to the axis you're looking at, right? So if we're looking at this axis, this now becomes our height, right? And so we take the height cubed, and this one is the side that is parallel to the axis about which you're rotating is your base, right? And that way you only need to memorize one formula. Either way, you end up with the same result, right? What are some other common shapes that we know the moment of inertia of? Yes? How do we know what axis to use? So, first of all, where do we see eyes? Where do they pop up in this class? Bending and transverse shear, right? And so you mentioned the neutral axis, right? Is our neutral axis always the axis that we establish the eye about? I'm seeing shrugs and some silence. I saw someone mouth some answer. Yes. Yeah, you are 100% correct, right? No matter what case you're dealing with, whether it's transverse shear or bending, it is always that neutral axis is the axis about which you're bending. Now, how do we establish the neutral axis? Right? In bending, it's kind of straightforward. At least it's straightforward to me. Is it straightforward to everybody? In transverse shear, is it straightforward? It's actually the same axis, right? Usually. Right? So in transverse shear, it is the axis that is perpendicular to the direction of your shear force. Right? Does that make sense? And then in bending, it is the axis about which that bending moment acts. Right? And so that is how you choose which one you do your eye about. Right? So if you had a bending moment that was this way, right, or this way, the other way, right, you would use this form, right, versus this way, you'd use this form. Make the sense? Yes. Okay. So what other common shapes do we know I for? Circles, right? What is it for a circle? 4th pi r to the 4th. Perfect. What about for a hollow tube, an annulus again? Right. And remember that not the same. This is not the same as this. Right? Those are not the same thing. Yeah, don't. Be careful, do not do this. This is wrong. Wrong. Where's my red? Wrong. Wrong. This one is right. Okay. And those are, I believe, the most common shapes You might, I was going to say you might want to learn the one for a semicircle, but what is it going to be? Half of that. So, well, so if it's half of that, what axis is that about? Not really, right? In that case, right, if you use I is equal to 1/2 of that, that's the axis remains the same, right? The axis stays here, which notice will never. That's not going to be your neutral axis, right? Because your neutral axis passes through the centroid. So the I about your neutral axis is actually going to be different for a semicircle. I don't have that memorized, ergo it's probably not that important. Yes. Yes. It does look really similar to J. What is J? There we go. So I is 1/4. J is pi over 2 r outer minus r inner, right? It's actually the same up here. So J is equal to pi over 2 r to the 4th. Who can answer that? What is J? Correct. J is the polar moment of inertia. In other words, it is the moment of inertia about an axis that goes through that cylinder or through that shaft. Where do we use that, by the way? Right, which is which load condition? TC over J is correct. And it relates to a load condition. What load condition? What is the T? Torque, right? It's torsional shear stress. Right? Are we all familiar with the 4 load conditions? When I say that, like, does everybody know what I'm talking about? Awesome. Let's go over those, because those are really important, especially for combined loading. All right. So are we now comfortable with I a little bit more? Again, if you were looking at more complex or composite shapes, such as I-beams, right? I, unlike a y-bar prime, is subject directly to the law of superposition, right? So in order to establish I's, you just need to add them up. Now the trick is you have to add them up about the correct axis. So you might have to do what? We did a bunch of it in the dynamics session. Parallel axis theorem, right. In other words, when you have an I-beam, right, that's a really bad I-beam, but you get the idea. When you're doing the moment of inertia about its neutral axis, right, if you just use the 1/12 bh cubed for this guy, right, that is his moment of inertia about his own neutral axis, right? In order to establish his neutral axis about, or his moment of inertia about this neutral axis, you have to then do parallel axis theorem, which in this case takes on the form 1/12 bh cubed plus area of this guy, right, times that distance times the centroidal distance squared. Yeah, again, this distance is neutral axis to centroid of your shape that is making up the composite. Okay? Now, we want to avoid parallel axis theorem as much as possible. So in the case of an I-beam, what can we do to avoid that? Exactly, right? We can, if this thing is symmetrical about the neutral axis, right, what we can say is, let's instead take this, big rectangle, do his I 1/12 bh cubed, and then subtract out 2 of these guys, right? 2 of this area right here. Because their neutral axis is in line with the overall neutral axis, you don't have to do parallel axis theorem. Does that make sense? My feeling is avoid parallel axis theorem as much as you can. Correct. Yes. If the neutral axis of your individual shapes that make up the composite lie along the neutral axis, the overall neutral axis, you do not have to use parallel axis theorem. If they don't, you have to use parallel access theorem, right? So for an H-beam, right, which is an I-beam turned on its side, surprise, surprise, right, it kind of works the opposite way. In this case, you want to add up all three, assuming you're going about this axis, right? You want to add up all three rather than subtracting, because now each of these guys has their neutral axis on the overall neutral axis. And in a T-beam, you're screwed, because you have to do parallel access theorem. There is no way around that for a T-beam. Are we? Yes. Go for it. Yeah. Yes. So the overall lesson here is that moment of inertia, the I, right, is subject to the law of superposition, asterisk. That asterisk being you must do it about the overall neutral axis, which may or may not involve parallel access theorem. So superposition, the law of superposition, what I mean when I say that, simply means that the overall blank, whatever property it is, okay, is equal to the sum of that property for all the individual parts, right? Certain properties are subject to that, certain properties are not. Moment of inertia is one of those properties. In other words, if you have a composite shape, right, something made up of smaller parts, then the overall moment of inertia is equal to the sum moment of inertia of all those parts that make up the composite. Okay. Yes, that's what we were doing in dynamics. We also established a lot of that because it works the same for mass moment of inertias too. Are we comfortable with those eyes now? Cool. So I'm going to take a real quick diversion from our scheduled agenda to talk about load conditions, because those are, I very, very much assume you're going to get a combined loading problem on this test. The reason I say that is because aside from chapter 3, right, which was material properties, chapters 1, 2, 4, 5, 6, and 7 all culminate together in chapter 8. So if we ask you a combined loading problem, by doing that, it tests your knowledge of essentially chapters 1 through 7, right? So it's one problem that almost covers the first half of this course. So it's a very good way to test multiple things in one go. So when I talk about load conditions, right? Load conditions are made up of two things. Has anybody been to a session where I've talked about what those two things are? I think you two have been there. Have you two seen the tree diagram that I draw? Okay, so if you've not seen the tree diagram, you have not had this discussion yet. So, load conditions are made up of two things: the type of load and how, or the orientation in which it is applied. So when I say type of loads, what options are there for types of loads? Axial loading is a loading condition. That's what we're going to establish. You're close. That's a good guess, but that's really for beam kind of stuff. This is a little bit more general. Both of those actually fall under the same overall type of load. Say again? I just heard someone. Moments is one of them. And then what's the other one? So if we're not applying a moment, what else can we apply? A directional load, which is called a? Someone said it. Force, right? Forces and moments. If you've noticed, I try and be very careful when I talk about what we're talking with. If we're not talking about a particular one, I will say a load, right? And so load can mean either a force or a moment, right? One is the quote-unquote rotational equivalent of the other. Okay, so those are the two types of loads. Now we're going to talk about how do we. We're going to talk about their orientation, right? So when we talk about the direction of a force, how can we discuss the direction of a force? We can say it is what? Relative to axes, right? we look at the axes about or on which these things happen, right? When we talk about forces, they literally happen on an axis, right? Or off an axis and thus have a combination or components along those axes, right? So if we have a coordinate system and we have a force acting along some of these axes, we establish certain load conditions. Now let's talk about moments for a second. How do we describe the location or orientation of moments? So that is the direction, and that is the most common way that we establish them, correct? But there is actually kind of a more specific way, because does clockwise or counterclockwise refer to any axes or any coordinate system per se? No, right? How can we establish an orientation relative to a coordinate system for moments? About, right? The axis that it acts about, right? And remember, can we represent moments as vectors? Yes, right? They are vectors that lie on that axis that they act about, right? Does everybody remember that from like, I think it's physics 1, physics 2, right? When you establish a moment, you do your right-hand rule, right? And your thumb points in the direction of the vector, and that is the direction of the axis it acts about. Okay, so now let's say we have a cross-section, right? And let's go ahead and stick a coordinate system on this cross-section, right? So where would be a good place to establish that coordinate system, the origin of that coordinate system? So you could technically put it anywhere. Where is it going to make sense? In other words, where do we a lot of times see things acting around? Centroid, right? Not center, centroid. Everything here is centroid. Everything has area, right? So let's put our origin at the centroid, right? And so let's establish some coordinate systems. So if we have x over this way, y over this way, and then we'd have z, positive z would be out of the board, right? Using a right-hand rule. So we have positive z coming out of the board. So how can we apply different loads to these coordinate systems? Let's talk about forces first of all. What are all the different ways we could apply forces to this guy? Right. Forces along x, forces along y, forces along z. Right? So which of those are going to behave differently from one another? Right. If we do a force along x and y, right? Mathematically, obviously, they're going to have different things, right? But they behave overall the same way, right? What do we call a load that acts like that? Shear. These are shear loads, right? Namely V, right? Transverse shear loads, right? And thus, if we have a load like that, it is a transverse shear load, right? What happens if it's along the z-axis? What type of load is that? That is an axial. And so that is the axial loading condition, right? So what we're going to do is we're going to establish a way to determine what combination of load and orientation creates what load condition. So the way I do that is the main thing that we look for in this class is what? It was the very first thing we learned to look for. Or learned to calculate, as it were. Stress, right? What types of stress are there? How many? Yep. Say it louder for the people in the front. Yep, shear and normal, right? Sigma and tau. So we're going to approach this from a tree diagram perspective, okay? So what the next thing is we have to determine which load conditions cause which type of stress, right? So what load conditions cause shear or normal stress? Actually, let's kind of work with this the other way. What formulas do you know that end in a sigma? What formulas? P over A, right? The very simple one. MC over I. Right. Perfect. Okay? And then which formulas did we learn that established shear stress? VQ over IT, right? You're correct. And actually, thank you for pointing that out. I'm going to actually change this to the more general form of my over I. C over I is not incorrect. That's just the maximum version of it. This is the general form of it. And then the general form of this one is T rho over J. Perfect, right? So these actually are these are the equations that establish the stress for our loading conditions. So now we need to establish what are those loading conditions, right? So over here in this one, what type of load do we have? Force, right? P is a force. Where is that load applied? So, yes, over an area, but remember how when we talk about the orientation of forces, right, we're looking for axes, right? Perpendicular to what axis? Like, remember that force has to lie on an axis, right? So which axis is that relative to the cross section? Yes and no. It was Z in the example we just put, right? I don't like using X, Y, and Z because we can name our axes whatever we want, right? We can name them Larry, Moe, and Curly. So I don't like students to get into the habit of saying X, Y, or Z axis. Let's try and be a little more specific, right? Yes, perfect, right? It is a force that lies on the axis normal to the cross-sectional face. So it is a force type of load, and it is on the axis, which is normal to the cross-sectional face, CSF. Okay? And this creates the loading, this combination is the load condition that we call, not shear. What was the name of the chapter it was in? Axial, right? The axial load condition is a force on the axis normal to the cross-sectional face. Okay. Now, let's look at moment, right? Or the next one, right? So first of all, what was the name of the chapter that this came from? Bending, right? So this load condition is called bending, right? Understand that the load conditions cause a stress, right? And each one causes a certain type of stress, either normal or shear, right? The two that cause normal stress are bending and axial, right? So the bending loading condition, what type of load is it? It is a moment, right? And where does that moment act? Which axis? Say again? So the neutral axis is defined as the axis about which it acts. So you're not wrong, but this axis, remember, notice that this axis we said it was, we established its position relative to the cross-sectional face, right? So again, relative to that cross-sectional face, tangential. Yes. There's not as good of a way of saying that, right? Is it normal? If you have if you have one that's about the normal, is that a bending moment? No, right? And that's what we're about to see, right? So these axes, so going back to our one here, right? So if we had, again, x, y, and z. Again, please do not get caught up on x, y, and z. That is just for this example, right? In this example, about x, y, or z, which one would cause a bending moment? X or y, right? Those ones we can say they are parallel or in plane with is kind of a better way of saying it, right? In plane with the cross-sectional face. So there's a moment that is about, notice not on, but about an axis, any axis that is in plane with the cross-sectional face. Okay? So those are the two load conditions, let me draw a line between them, that can cause normal stress. All right, so now we shift over to shear stress. So first of all, this one right here, what chapter was that from? Yes, the name of the chapter I'm looking for. For VQ over IT was from Transverse shear. Can you see this board? Okay, just making sure because my angle's a little weird. Right, so the load condition we are establishing is now the name of the load condition. If it was from the transverse shear chapter, the load condition is transverse shear. Yeah, hint, hint, the names of the chapters are the load conditions. Right? So, what type of load causes this? A force, right? V is a force. And where does that force lie? On which axes? X or Y, in our example, right? So X or Y are these guys, right? So in this case, it is on, not about, but on an axis, which is in plane with the cross-sectional face. Okay, so our last one is what load condition? So we just did transverse shear, so this one is torsion. Perfect, right? So what type of load causes this? Moment. And where does that moment act? So X or Y we established as this one, right? So X or Y is a bending moment. Exactly. This is about the axis, which is normal to the cross-sectional face. These are your four loading conditions, right? These are super important, right? Because when we get to combined loading, right, when you do a combined loading problem, what you do is you do method of sections to establish the type of loads, right? And so, for example, if you have like a bent beam, right, and you have some load applied here, then you do method of sections to find out, okay, what internal stuff is happening back here, right? What moments do you have? What forces do you have, right? Everybody remembers how to do that? Okay? And so then, once you establish those forces and moments, you then look, okay, what axes are those acting about? Where are they loading? Where are they acting? And now you have your type of load and its orientation. You can establish which equations to use. Right? That is how you solve a combined loading problem. That's how you approach them. Right? Start with your statics, right? Just solve for what the moments and forces are, and then you can use this T-chart or tree chart right here to decide which stress equations to use. Yes? Yeah, so this one is normal stress. Correct. Yes, so this is axial. Yep. So which one is this one? Transverse shear, right? Yep. Perfect. Yeah, so those are the names of the loading conditions. Yes? So can we add all normal stresses that are acting together at a single point? Yes, you can, right? So if you're looking at a point, a specific point on this guy, right, and it has stress caused by both bending and axial, right, or it has shear stress caused by both transverse and torsion, you can add them up to get the sum total, right? And again, now the thing with that is you have to establish a directional system, right? Because a transverse shear this way and a torsional shear this way, right, are in opposite directions. So you'd subtract them to find the overall magnitude. Does that make sense? But yes, that was a good question. And yes, you can add, if you have both of these at a point, you can add them, their results up. Yes?
Just to clarify, that's used with indeterminate beams, right? Because you can't solve using one of methods, you have to use superposition.
So in solid mechanics, because I know you're from mechanics of materials, we don't do statically indeterminate as often. So to an extent, yes, but you need some, at least from the perspective of solid mechanics, you need some more stuff as well. We usually do that. We usually approach statically indeterminate things from the perspective of deformation rather than from stress. So I don't want to say yes, definitively you can use superposition of stress to solve for statically indeterminate. You can use superposition of deformation to solve for statically indeterminate. Yes, in the sense that we just talked about, right? So a lot of times what they will ask you to do is, okay, here's your point, right? Draw the stress element at that point. And so when you draw the stress element, if you have both a torsion and a shear stress like we show here, right, they resolve into a single shear stress that you would show on the element, right? So your element, right, would look like this, right? And where this tau here is the combination of those two values. Make sense? All right, so are we comfortable now when I say load conditions, what I'm talking about? Cool. Sorry that I was doing that beforehand without checking if anybody knew what it meant. All right. Yeah, this tree chart right here is essentially chapters 1 through 7 summed up into a single thing, and it is the main method for solving all of chapter 8. Yes?
Can you go over that bottom portion again?
Right, so this bottom portion just describes how, right, a load condition is made up of a type of load, so either a force or a moment, and where it is applied. So a force that is on an axis that is normal to the cross-sectional face, right? So if this is our cross-section, here's the normal axis.
I got it.
Yeah, got it?
I just wanted to know.
Yeah, the CSF is cross-sectional face. Yes. All right, so does everybody who wants to take a picture or have that written down, have it written down or have a picture of it? Am I good to erase? Am I good? Cool. All right, so now let's jump back to our agenda a little bit. So we're now going to talk about Mohr's circle. Okay. So first of all, again, I want to approach this from a more conceptual base because there's some things about stress transformations that always get students. So first of all, does everybody understand why we do stress transformations, what they are and what they represent? Okay, does anybody know why we do stress transformations? Yes, essentially yes. So essentially what we're looking at, right? Has everybody taken properties and structures of materials or a similar class? Okay, so you have not taken anything. So we're going to do this from a baseline perspective, right? So solids are made up of what? Yes, atoms/molecules that arrange themselves in a crystal lattice, right? And so in properties and structures, you talk about the different types of lattices, right? There's ABA, ABC, a whole bunch of different options, right? And each one of them has these things associated with them called slip planes. Do we remember those? And a slip plane, right, is essentially a plane or a direction along which the molecules are likely to slip past each other because of how the bonds work. Without going too much into chemistry, the bonds are more likely to break along certain directions, right? And thus the molecules are more likely to slip past one another in certain directions. So going back to this class a little bit, right? Does everybody know what a stress element is? Right, the little squares that we draw, these things? Oh, is this the dead marker? This is probably the dead marker. No, that's the dead marker. We'll keep one. Well, then we'll switch to green. Time for a color switch. Okay, the little squares that we draw, right? And we have this stuff happening on them, right? So first of all, does everybody know what those are and what they represent and how we use them? Lots of blank stares, cool. So a stress element represents an infinitesimally small point, right? In other words, all those times that they ask you what is the stress at this particular point, right? That point has no dimensions, right? Or has differentially small dimensions, right? And so that infinitesimally small point we can show as a square called a stress element, right? Now, even though this stress element is infinitesimally small, we can also consider that it contains an infinite amount of stuff, right? In other words, molecules or atoms, right? And how did we say those molecules or atoms are arranged? In a lattice, right? So they're arranged in some lattice, right? So just because we are looking at the stresses, right? These stresses are obviously along coordinate axes, right? Let's call them x and y for now. Right? Just in this example, please don't get hung up on x and y again. Right? But just because we're looking at this in terms of x and y, does that mean these molecules are most likely to fail along this x and this y? No, right? They could fail along that line, right? Or along I drew this lattice very poorly, but you get the idea, right? There are different lines, different slip planes between these molecules that this could very well fail along because you need a different stress, or a different stress is experienced along that plane, right? And the way we calculate that is through a stress transformation, right? So in other words, we reorient our stress element, right? So here's now, here's the original x and y. So now we've reoriented to what we call x prime and y prime, right? And so now we're discovering, okay, what are the stresses experienced under the same load conditions, right? But now we're looking at a different version, a tilt or a turn of our stress element. Note, in the book, it's actually very common, instead of turning the whole element, they just cut the old one, right? They like to do things like this, right, where they cut it like that, okay? And so notice on this one, you still have your original, your x and your y, right? But here's your prime, and then 90 degrees from that is prime, right? Okay. So that is what we do stress transformations for. Now, without going through too much, right? We understand that there are equations so that whatever the angle between your original axes and your new axes, right? Whatever angle that is, there are equations to solve for your stresses along x prime and y prime, right? We know that those exist. The reason I'm not going into them too much is because I don't have them memorized well enough that I feel comfortable telling that to you. And like I said, I don't have my textbook here. But if you look in the stress transformations chapters, those are the first kind of equations that they establish. And those equations are for, we might have them here. That is that, yes. Right? They look generally, they take on the general form of stress x plus stress y over 2 plus stress x minus stress y over 2, whoops, 2, cosine of 2 theta plus tau xy sine 2 theta, right? Where this is your stress in the x direction in the original orientation. This is your normal stress in the y direction in your original orientation. This is the shear stress along the xy in your normal orientation. And the theta, sorry, not sigma, theta is the this change, right? The angular change. Now remember, in this formula, so first of all, this is particularly for the x prime direction. In the y prime direction, right, these become subtractions, and the tau x prime y prime is a little bit more complicated. But look for something. Go to the textbook and look for the equations in this form, right? And remember, using these, what is positive and what is negative for theta? This way is which way?
Okay, clockwise is negative.
There you go. Clockwise, so like this one would be negative. If we were to use this theta, this would be a negative theta. This one, right, where we rotated up, this is a positive theta, right? So be very careful when you're, especially when you're cut ones like this, always draw the original axes first, then draw your new ones and figure out which way you're rotating, right? Because a lot of times they will give you just a random angle here, and that random angle is not necessarily your theta, right? You have to go through the actual geometry of it yourself. Okay, so that is how we do a general stress transformation. That can be to any what we call stress plane, right? And the stress planes are represented by these thetas, these angles. Now, when we do stress transformations, we look into some very specific cases, or we look for some very specific stresses. Does anybody know what those stresses are called? Yeah, I heard it. Principal, right? What are our principal stresses? What's special about them? They are, which means that they are what as far as normal stress is concerned? They are the maximum and minimum normal stress that is experienced throughout any rotation, right? If we rotate this thing through, technically it's only through 180 degrees, but it's symmetrical when you rotate it back. So if you rotate it through the 360 degrees, they are the max and min normal stresses that are experienced. What else is special about them and the plane on which they exist? What do you mean it's the same? So yes, principal stress 1 and 2, right, the max and min, do occur on the same plane. I think that's what you're going for? Yes, but there's also something else special about this plane. What type of stress are those? Or did I just say they were? Normal, right? What is their shear stress on that plane? There is none, right? The principal planes occur on, or the principal stresses, I'm sorry, occur on the principal plane, and on the principal plane, at this rotation, there is no shear stress, okay? There is such thing as a max shear stress as well, and there's a plane of max shear stress, but it is not the same, right? You might have normal stresses on your max shear stress plane. Okay, so now let's go ahead and talk about how do we create Mohr's circle. So this is what I will tell you about Mohr's circle. First and foremost, it is, can we calculate principal stresses? Woo, that's stuck on there, nice. Can we calculate principal stresses and maximum in-plane shear stresses and all these other stuff from just equations? Yes. Okay. So what is Mohr's circle then? Mohr's circle is simply a graphical representation of all of those equations. What that means, you are not going to get anything extra out of drawing Mohr's circle, right? It doesn't give you any more information than just the equations do. However, there are some folks who learn better or can understand things better with that graphical representation. Additionally, it shows in a kind of coordinate system-ish form how all these things behave, and it establishes this very pretty kind of relationship between the rotation through which you rotate your element and the stresses that are established. Okay? Additionally, it's super useful when we get to the 3D case and do that 3D Mohr circle. Right? So, first and foremost, what we have to explain is everybody understands that in stress transformations, we only deal with planar stresses. Do we understand what that means? Thumbs up for yes, thumbs down for no. Okay, so a lot of thumbs in the middle. So planar stresses, when I say planar, what does planar mean? In a single plane, right? Which means we only use how many dimensions? 2, right? So when we do stress transformations, we only look at stresses applied in 2 dimensions, right? We don't have anything happening in this 3rd dimension, stress-wise anyway, okay? Now, when we get to again, we will talk about 3D Mohr circles. In a 3D Mohr circle, we are analyzing it from a 3D case, but the stresses themselves still only exist in a plane, okay? That's an important, keep that in the back of your mind. It's a special tool we'll use for later. All right, so when we do Mohr circle, right, let's start with this general case, right? So in the general case, we have sigma x, sigma y, and tau xy. And for the purposes of this demonstration, let's assume stress x is greater than stress y, or sigma x is greater than sigma y. So when we graph anything, right, what is the first thing we need to graph things? Yes, kind of, but there's something actually even more basic than that. We need a coordinate system, right? We need axes, right? So what are the axes that make up the coordinates on which we graph Mohr circle? So that is the coordinates on this thing, right? That's the axes on here. That's a little, so that's these guys, x and y. This is a little different, right? These are not actually x and y coordinates. They are, right, they are normal and shear stress coordinates. Now, one thing that I will note is that your textbook establishes downward as the positive shear stress direction. I have no idea why it does that. It doesn't make any difference to your analysis if you do it the other way, because in this class, Mohr circles are always going to be symmetric about this normal stress axis. So it actually doesn't matter which way you go. But just to keep with the convention of the book, positive shear stress is downward. Okay? So now we need points, right, as everybody said before. What points do we graph if we are given this element? So we need to establish those points, but based just on this, do we know what they are? You can calculate them, right? So you could go through the equations. Let's do this the other way. Let's draw Mohr circle first, and then from Mohr circle, let's derive the equations. Okay? So how do we graph this thing on stress and strain, or normal and shear coordinates? Right. Right. So in other words, do we see sets of coordinate pairs anywhere on this thing? Or anything that we could use as coordinate pairs?
The shear stress is like the counter up in the kitchen, the counter's above, and then like the clock.
I've never heard anything like that. Let's start with where do we get our coordinates from? The corners?
You got your shear stress value, then you got your sigma x value.
Yeah, right? So we can use a side, right? This is a coordinate pair, and this is another coordinate pair, right? We have a sigma and a tau, right, which is what we need to graph. So let's graph these things, right? So for this side, sigma x, is it positive or negative? Positive. And it's out here somewhere, right? Now, for tau xy, is this particular one positive or negative? Positive, right? Because it's going counterclockwise, right? Essentially. That's the way I like to think about it, right? So this individual one is positive, right? So we go over to sigma x and down tau xy. There's our first point, right? So let's graph this other one, right? So is sigma y positive or negative? Positive. And this tau xy, or in this case it's technically tau yx, right? Is he positive or negative? Negative, right? This particular one wants to rotate clockwise. So that one is negative. So we go out to sigma y, which we said is smaller than sigma x, and we go up. The magnitude is the same, right? So the distance from this axis is the same, but it's negative, right? Okay, so if we have 2 points on any coordinate system, what can we create? A line segment, right? So let's do that. There's a line segment. Okay. So what is the end goal of what we're trying to graph here? A circle, right? So what kind of line objects or line dimensions are associated with circles? Diameters and radius, right? So in this case, remember that I said we are symmetric about the sigma axis, so this would be the diameter, right? So in order to create the circle, all we have to do is spin that diameter, right? Spin it around. Ooh, a bad circle there. That's Mohr's circle, right? Now, this is a very skeletal Mohr circle. We don't have a lot of information about it, so let's try and establish some information, right? So what is the most important point of any circle? Center, right? So let's try and get the center. Namely, note, we are going to find the value of the center as a location, a distance from this origin, right? This 0, 0 point. So how can we find the value of this center point, which we know, by the way, is where that diameter crosses the sigma axis, right? Because we've already established that we're symmetrical about that point. So how can we find the value, the sigma distance of that from 0? Say again? Kind of, you said it. It is the average, right? We know that this point here and this point here, right? We know if we draw that, right? This is sigma y, that distance is sigma y, that distance is sigma x, right? So we know that the point in between them is the average. So the average, or the center point, is sigma x plus sigma y over 2, right? Okay, if we have a center, right, what other values can we find? Let's find the radius, right? Because we already have a diameter. We don't have a value for the diameter, but we have one drawn, right? So let's find the radius, right? We like radii, usually, right? They're a good thing for circles. So how do we find that radius value? You're close. You're very close, right? Why are we using square root of something squared? Kind of. That's magnitude of a vector, right? We're not necessarily looking at a vector per se. Pythagorean theorem, right? We have some right triangles here, right? We know this height here, right? We know that that's what? What's the value of that height? Tau xy, right? And so now we just need this. So what is that distance? So we're looking for this distance right there. Sigma x minus the center, right? So it's sigma x minus sigma x plus sigma y over 2. If you do the algebra there, I hope you all can do that, you end up with sigma x minus sigma y over 2. All right? And so we can now do Pythagorean theorem and say that our radius is equal to square root of sigma x minus sigma y over 2 squared plus tau xy squared. Okay, so now what are some other points that we can establish? We can now get these max and min, right, where the circle intercepts that axis. How can we get those? Center plus or minus your radius, right? So you can say that. Now, hold up a second. What did we say were the max and min normal stresses on the circle? They had a name. Principal, right? How are the principal stresses denoted? What is their subscript? 1 and 2, right? So we can say sigma 1 or 2, right, is equal to the center, sigma x plus sigma y over 2, plus or minus the square root of sigma x minus sigma y over 2 squared plus tau xy squared. Have we seen this equation somewhere before? This is the equation that the book gives you. This is, right? Now you can see how it graphically relates to Mohr's circle. It is literally center of the circle plus or minus the radius. Note, what else is the radius equal to? So these are the max and min normal stresses, right? What other point is important? Exactly, right? The two of you said it, max shear stress, right? We usually don't care about min shear stress per se because we know that they're the same in magnitude, opposite in direction. So we just care about absolute value. So we look at the max shear stress, right? And that's equal to the radius, right? And again, if you look in your book, it calls it the tau in plane max is equal to stress x or sigma x minus sigma y over 2 squared plus tau xy squared, right? It's the second half of that equation. Graphically, it all relates. So now do we understand, given a single, so let's go back through that process a little bit, right? So from the stress element, what do? Not your max and mins just yet. Right, we establish the coordinates, right? We take each side as a coordinate, and so we say, okay, let's graph this normal stress and this shear stress that is associated with it, and let's do the same on the other side, right? So we graph those 2 points, then what? Drew the line, connected them with the diameter, then made the circle, right? And from that circle, you can establish your center, your max and min, or otherwise known as your principals, right? And your tau in plane max. So we'll get correct. We'll get back to what in plane means in a second. I do want to talk real quick about angles, right? So each diameter on this thing, what does that represent? So, right, if we were to, remember how we rotated the diameter through 360 degrees, or through 180 degrees, really, to create the circle? So what does each of those diameters represent then? It's closer to what he said, right? The slip planes, right? Those are the different planes, right? Remember, the whole thing that we're doing is we are rotating this element through some 360 degrees or something like that, right? So each of these diameters represents one of those planes, right? With this one being your principal plane, your theta p, right? This one being the theta that we originally saw it in, and this one, right, being the theta s, the plane of maximum shear stress. Okay? Now, here's the trick. The thetas in between them on Mohr's circle, does anybody know what they're equal to? In other words, the angles between different planes, are they equal directly to theta? No. What are they equal to? 2 theta. Good. Other way around. It's and we got it up here. It's 2 theta, right? Which is why if everybody goes back and remembers the general equations, we had cosine and sine of 2 theta. This is where that comes from, right? The angle that you see here represents twice the angle you'd have to rotate the element itself through, okay? And so, notice the angle between the given plane and the principal plane is called what? It's up there. Theta p. Perfect. And the angle between the given plane and the plane of max shear stress is what? 2 theta s. Perfect. Now, what does that mean about theta p and theta s? Close. 2 theta p and 2 theta s add to 90. So theta p plus theta s adds to, other way around, do the math. So 2 theta p plus 2 theta s equals 90. Right, theta p plus theta s equals 45. Always, right? It doesn't matter what stresses you experience. It doesn't matter the material. It doesn't matter how much force you apply. Now remember, the theta p and theta s, right, might be different distances away from your established or your given plane, but they are always 45 degrees from one another, right? So once you find one of those planes and the angle that represents it, you can automatically find the other one just by doing this equation right here. Okay, so now let's talk about in-plane. What is this in-plane and what do I mean by it? Why does tau get an in-plane? Yes? Yes? You could, I wouldn't. Here's the thing. If your original one is given at a rotation, actually you can just kind of establish it this way. You can think of it as, if your original one is like this, right? Here's your theta, right? So where do you graph the points? Yes, that's actually exactly what you can do. When drawing Mohr's circle, there's no reason for it to. It doesn't matter how you graph those, right? If they give you this and this, right? It doesn't matter what angle that is at. The process remains the same. You just take those, graph them, and so you just establish a different diameter, right? Does that make sense? Answer your question? Okay. So going back to this discussion on the shear stress, what do I mean when I say the max in-plane shear stress? That is a good guess. It is not correct, but a good guess based on what it says. So remember that we are dealing with planar stress conditions. So this is the tau max rotating which way? And I don't mean counter. In other words, how have we been rotating this element? Right, about this z-axis, right? Is that the only way we can rotate this element? No, right? We can rotate it like that, which is what we did, or we can rotate it like that, right? Or we can rotate it like that, right? We can rotate it and analyze it in 3 dimensions, right? And so that's where we establish the 3D Mohr circle. Now, again, I'm going to emphasize this point. We are analyzing or looking at the element rotated through all the dimensions. The stress conditions themselves stay within a single plane, which means what about this third plane and the stresses acting on it? Are there any? No, right? So what ends up happening is, in planar stress conditions, you actually have three principal stresses, right? The two that we calculated here, and what is the third one? Somebody said it. I heard it. 0. Your third principal stress is always 0. Okay? Note, your third principal stress is always 0, not principal stress or principal stress subscript 3 is 0. This confuses the crud out of students. The convention for labeling your principal stresses is principal stress 1 greater than principal stress 2 greater than principal stress 3. Okay? What that means, these the ones that you calculate. The subscripts given in the equation are 1 and 2, but it is not necessarily stresses 1 and 2 that you're calculating. Right? If both of these turn out to be negative, what is your third principal stress? Always. Your third principal stress is always 0, right? Is 0 greater than 2 different negative numbers? So your third principal stress is principal stress 1, right? The subscripts do not get caught up on the subscripts. They're the largest one value-wise is 1. The second largest one value-wise is 2. The third one value-wise is 3. Right? So no matter what these numbers calculate to be, the subscripts just come after that, right? So the third principal stress, whatever one you didn't calculate here, is 0, not necessarily principal stress 3. Does that make sense? Okay. That confuses a lot of students when we go through this, and so I wanted to make sure that that's not happening here. So I'm going to erase some of this. So now what happens, right, where we've drawn our Mohr circle, we have drawn what is called our in-plane Mohr circle, i.e. it is the Mohr circle that represents all the rotations of this element within the plane that these stresses are acting, right? And so our third principal stress is where? At 0, right? And so now we can draw 2 more Mohr circles, right? Let's just connect some dots. We have a dot here. We have a dot here, right? The 2 calculated principal stresses, the third principal stress. Let's connect the dots. Circle, circle, right? Those are your out-of-plane Mohr circles, okay? Now, in this case, the absolute maximum shear stress, is it within the plane or is it out of plane? Out of plane, right? It's on one of these out-of-plane circles. This was our original in-plane circle. This is an out-of-plane circle, right? So the absolute max is out of plane. That's what we need to look for when we do our 3D Mohr circles, right? We don't really care per se about the normal stresses, right? Because we're already calculating max and mins of those, right? Because either one of these guys is always going to be the max, and then the min is either the other one of these or it's 0, right? So we already know the max and mins for normal stress. So we care about in-plane and out-of-plane shear stress and which one is absolute maximized. All right? So do we understand now what Mohr circle is and why it's established? Okay? As I said before, it doesn't give you any extra information over the pure equations, but it's a nice graphical representation. Yes?
And so that's why sometimes you'll have a Mohr circle that has the origin point in it based off of whether or not the sigma y and sigma x are positive or negative. That will determine where your Mohr circle is located.
Exactly, right? This can determine it, or this can determine it, right? Both of these might be positive, but one of your principal stresses might be negative, right? If let's say sigma x was really, really small, right? What might happen is this circle may come over here a little bit, right? And so you might have a in-plane Mohr circle that straddles that axis.
That's why it's important to get your coordinate points first before you even draw a circle.
Correct, correct. So this circle, right, is the in-plane Mohr circle. Ergo, it is the circle that represents all the rotations of the element within the plane that the stresses are acting. These two are called the out-of-planes Mohr circle. They represent some rotation that is in a plane, right? The plane contains one of the axes on which stress is acting, but not the other one, right? So if this one were made in the xy plane, we could say that this one was one of the two, either the xz or the yz, and this one is either the yz or the xz. Make sense? Okay. I don't want to spend too much more time on this because I do want to get into the Macaulay functions a little bit. So are we more comfortable now with Mohr circle, no pun intended?
Absolutely.
Awesome.
So why is it that sometimes that they'll be epsilon instead of sigma?
Oh, let's real quick talk about strain. That's for a strain transformation, right? Strain transformations work the exact same way, actually. The only difference, and this kind of a big difference, anytime you see a tau, right, what is the strain, what is shear strain? What's the symbol for it? Gamma, right? So remember that normal strain is the epsilon, shear strain is gamma. So anytime you see a tau, right, the equations are actually all the same. You just switch them over to the strain versions, right? But anytime you see a tau, it becomes gamma over 2, right? And that's the only difference. And then the Mohr circle, the coordinates that you graph it on are epsilon and gamma over 2. Okay, otherwise, the process is the exact same thing.
That really
Yeah, it's just one is stress transformations, one is strain transformations. All right. I'm going to erase some of the stuff on the side so we can start working on the Macaulay functions. Woo! Okay. No problem. So, Macaulay functions are a way of finding what? What chapter are they in and what are they used for? Right, and they're used to solve for what? Yes, deflection, right? What is called deflection, right? Or the elastic curvature is the name of the equation itself, right? So let's quickly talk about what is deflection, right? Obviously, it is how much a beam deflects or goes off of its normal straight path, right? And so mathematically, how do we establish it? Not necessarily from the neutral axis per se. So remember that we have, right, here's our beam, right? And so we apply some load to it, and so it, yeah, that was a bad deflection, right? It deflects like that, let's say, right? So how do we, right, what we're looking for is how much distance that is, right? So how can we mathematically find what that is? Right, you take the moment equation, right, moment as a function of x, you integrate it twice, right? Well, so let's see, you integrate it once and what do you get? Right, you're both correct. It's called the slope, and it's called sigma, right, as a function of x, or theta, sorry. You integrate that, and now you get your deflection, right? Please note, this is the Greek letter nu, okay? It is not lowercase v. Lowercase v is Poisson's ratio, okay? I've actually had students come to me and like, yeah, in this chapter they were talking about Poisson's ratio. I had no idea what it was. Like, no, it's its own thing. It's a new, it's new, actually, literally. Okay, note, values of these have one more thing in them. What is it? Constant of the form. So there are constants of integration that we have to solve for, but the actual values, there's also something very important. It's another constant. EI, yes. So the way that it's done is EI times this is equal to the derivative, or the integral, right? So EI times the slope value is equal to the integral of moment, and vice versa, EI times nu of x is equal to the integral of slope, right? So when you actually do your integration, to solve for any actual values, you have to plug in x, and then you have to divide the integral part by EI. Make sense? Otherwise, you're going to get a really large number. If you are looking for a specific slope, yes. If you're not looking for a specific, for example, if it just gives you something and says, find the deflection at this point, you don't need to divide the slope here because it's a constant, right? So it comes out of the integral every, you can consider it like this, right, as 1 over EI moment of x, right? But because that's a constant, it comes out of the integral. And so it just kind of travels down. I would write it at every step just so you don't forget to put it in at the end. But you don't need to calculate it with every step per se. Okay, so as we established, right, there is the double integration method like this. So our friend there, I'm sorry, I did not get your name, with the gentleman with the hat who's in mechanics of materials. What's your name? Jorge. Okay, so Jorge was talking about when we can do this method, right? This is what I like to call the successive integration method. And all you have to do is, from your knowledge of statics, find the moment equation, right? So you do your method of sections for each, for however many sections you have, and you can integrate directly from that moment. Why is that not too helpful, or not too useful, I want to say? Yes, right? If you have a beam, right, let's just do a very simple beam, subject to loads like this, right? Is the moment equation here, here, and here the same? No, right? You can't describe this as a single moment function. In other words, you have to do this for every single one of those moment functions. And if you're asked to find the deflection of a point here, you have to know specifically his deflection equation. It also does a lot of crap with those constants of integration, right? So every time we integrate, so we have 1, 2, 3, 4 different behaviors of this moment, right? The moment equation behaves 4 different ways. So how many constants of integration do we end up with when we do when we do 2 integrations for 4 moment equations? You end up with 8 constants of integration, right? Way more than we want to solve for. Now that's where discontinuity functions and the Macaulay functions come in. So the Macaulay functions are really nice because they allow us to write the moment equation as a single function of x. They're defined in this way. So okay, so can someone tell me, someone translate this math jargon into English? C is a constant, yes. Not a constant of integration, just that is a constant based on the load, the type of load, right? So we have a constant, and then what's happening? Right, it's a piecewise function, right? And so what these special brackets mean is that at any point before a, this entire function is equal to 0. At any point equal to or after a, this function is equal to what it looks like, right? Just as if they were normal parentheses, okay? And so we can establish moment equations based on some known functions. If you go into your book, there's actually a table that for specific load conditions establishes what their Macaulay function looks like. Okay, I don't want to go through all of them right now, but there are specific, the different types of loads establishes your C and your N, right? Your A is your location from the origin that this load happens. In other words, if we had a cantilevered beam like this of length L, right? The load, actually let's do this, right? Where the load happens at 1/2 L over 1/2 L, right? So in this case, the Macaulay function, okay, what's the first thing you need to do when establishing Macaulay functions? You do boundary conditions, but that's not necessarily the first thing. What type of forces? What is the force here called? It's got a special name. Reaction, right? You have to do your free body diagram and do your reactions first, right? So you'll have a moment reaction and a load reaction like that, right? So there's your free body diagram. So now you start from the left and go to the right, okay? So we have a moment. Let's call the moment M, and let's call these guys value P. Right? So what happens is, for a moment, okay, the Macaulay function takes on the form M, so whatever the value of the moment is, times x minus a. So our a in this case is 0, right? This moment happens at point 0, right? Times up to the first, right? So this is it for the moment. Now, if I'm not mistaken, this might be negative based on this convention. If you look in the book, when you look at the charts, pay very close attention to the direction the arrows are going. It establishes the positive convention, right? And what you'll notice is upwards is the positive convention for positive, okay? And that's because you're looking at the internal stuff, and so going from left to right downwards is positive, right? And so the internal moment, or the internal thing that an upward force causes is downward, so this is positive. Does that make sense? So if the applied load is upward, the Macaulay function is positive, okay? Now for moments, this way internally is positive, right? So if we have a moment that's this direction, the applied is clockwise, so the internal is counterclockwise, so the Macaulay is positive, right? So this one is applied clockwise, Macaulay is positive. This one is upwards, so we have plus p times x minus a, which again is 0, and this time it's to the second power. Right? And then we have another point load, right? We go along the beam. So now we subtract, because this point load is applied downwards. So minus p times x minus, now we start at L over 2, right, to the second power. And that is your moment equation. Okay? This describes your entire moment as a single equation of x. Yes? This too? That is simply because of the type of load, right? So actually, no, I'm sorry, I think I'm wrong. I'm sorry. Moments are to the 0 power. Point loads are to the first power. Sorry. Yeah. If that was your question, because in the book it is a 1, the book is right. I was dumb for a second. Yeah. Point loads are to the power of 1. Freestanding moments are to the power of 0. Uniformly distributed loads are to the power 2. Linearly distributed loads are to the power 3. And you will not, we won't go above that. Yes? Yes. And it what? Yes, and that's the exact next thing I was going to hit on, right? So for distributed loads, for a uniform distributed load that goes like this, right? These take on the form actually, let me show the positive convention. So if it's going up, right, I will in a second. Let me establish the equation first, and then we'll do the specific case. So if it goes to the end of the beam, right, this takes on the form, if this has a maximum height of W, or a distribution of W per whatever, right, it takes on the form W over 2 x, let's call this point A, right, here's 0, A, B, right, so x minus A to the second power. Now, if we keep going, what happens if the beam keeps going? Okay? Does this establish an end condition? No, right? There's no way to tell. I like to think of Macaulay functions almost like a computer program, right? This computer program doesn't know when to stop, right? You haven't told it, stop. So how can we get rid of force that's, right? This function assumes that this goes all the way to the end of the beam, when clearly the load does not. So how do we take care of that? Yes, right? We essentially do equal and opposite, right? So if this one is up and it stops at B, right, this function sees it as it goes like this, right? But in reality, this part isn't there. So we can get rid of that with equal and opposite. In other words, establishing a ghost load that is now starts at B and is opposite in nature. So the Macaulay function for this, right, that stops, still going this way, which starts at A, stops at B, right, the moment equation for it is W over 2 x minus A squared minus, right, because this one was positive, so minus W over 2 x minus B squared. Okay? This is it for a single load like that. Okay? Now, real quick, let's talk about the horribly disturbing case of when we have a linearly distributed load that stops before the end of the beam. Right? In other words, what happens if we've got this guy? Okay, so once again, the Macaulay function doesn't see the end of this, right? So it assumes that you continue this way, right? You continue at the same rate from that same point. So the Macaulay function for a single linearly distributed load that does stop at the end of the beam is, if it has a slope of lowercase m, it is lowercase m over 6 x minus a to the third, right? So how do we get rid of this portion of the load that is not really there? In other words, what does our ghost load have to look like? Right, so it is a combination of what? Right, it's a combination of a uniform distributed load and a linear distributed load. In other words, you have to so if this is positive, you have to subtract out, right? Whatever this height value is, whatever it reaches at its maximum point, that is your W, right? So you get that W over 2 x minus B squared, also subtracting out. Now you have this linearly distributed load of the same value. So same slope, but now it starts at B. Right? All three of these are for a single linearly distributed load that does not end at the end of or that ends before the end of the beam. Right? These things are a little bit of a monster. But do we see, right, without memorizing the equation too much, do we see how we establish this, right? Why we have these two ghost loads and how the combination of these two ghost loads get rid of the load as if it continued as a linearly distributed load. Yes?
So then when you add everything together, you integrate your L, you zero the L value with the entire length of the beam?
Correct. And so when you integrate these things, Macaulay functions integrate very nicely in the fact that you don't actually care about what happened. The internal part just stays the same. So when you integrate this guy, he just becomes, right, this goes over 1. So you have m x minus 0 to the first, plus this guy goes up to 2, so p over 2 x minus 0 to the second, minus p over 2 x minus l over 2 to the second, right? Whatever's inside of the brackets does not change. You don't have to deal with it when integrating. Yes, good catch. Plus C1, right? And so then you get, this is your slope equation, you integrate again, and you get your deflection equation. I only have about like 30 seconds left, so I'm just going to give you the boundary conditions, unfortunately, right? Boundary conditions are established by your types of supports, right? So at a fixed support, right? Fixed supports block every kind of motion, right? You can't go up and down, and you can't do a moment, right? In other words, both your slope at that point, let's call it 0, right? And your deflection, both of those are equal to 0 at a fixed support, right? Because you can't rotate and you can't move up and down. At a pin support, right, you can't move up and down, but you can slope, right? There's no restriction on moment at a pin connection. Therefore, you know that the deflection is 0, right? But you don't know anything about the slope necessarily. Same thing at a roller, right? Now, in reality, can you come off of a roller vertically? Yes, right? Because a roller doesn't technically have a support or a fixture like that. But in the case of academics, we usually say that roller connections have a vertical reaction, right? And so we can, at roller connections, you can establish this same thing, right? You know that the deflection is 0. You still don't know anything about the slope, though, because once again, the slope, you are allowed to bend around a roller connection. Does that make sense? All right, and so you can use those boundary conditions, right? This isn't necessarily always 0. This is at whatever location the support is at, you know that those are 0. Okay, and so you can use those boundary conditions to solve for your constants of integration. That is unfortunately all the time I have for tonight. Thank you all very much for coming out, even though it was a very late session. I do have to let you know, on the ends of the tables here, there are some surveys. If everyone could please fill one out really quickly and then just leave them on the edge of the table. They're used for like some metrics that SARC collects. Very best of luck to the rest of you, and thank you all for coming out for my very last SARC anything. So I am graduating. This is the last thing I will ever be doing with SARC. So thank you all. And best of luck to you on this exam, and all of your exams. Thank you for saying so. I hope it seems like it went a little bit better than dynamics. That was a bit of a roller coaster, but